Of course, as with the other one, what if you want to do something for a composite area? You have to work a little bit harder. So let me explain what I mean. Let's say you have a rectangle, and you know, and you have the centroid of this rectangle. You can look in the back of the book and you can see the moment of inertia about the centroid. So this tells me the centroid is x bar y bar, and I x bar, which is the moment of inertia about this line, is bh cubed over 12. So this whole thing is b, this whole thing is h. So I x bar is bh cubed over 12. I y bar is b cubed h over 12. So those things are easy. But I don't want it about the centroid. Suppose I want it about some other point. What the heck do I do? One way to do that is to recompute and integrate, because now left, right, top, bottom have changed. So the basic thing, moment of inertia is different. Because left, right, top and bottom have changed. Right? But I don't want to recompute it. The thing is, if I know the moment of inertia around the center of mass, I can compute the moment of inertia about any other axis. This is called the parallel axis theorem. It says, if I want the moment of inertia about a non-centroidal axis, this is not in the centroid, I first find the moment of inertia about the centroidal axis and then add to this the area times the axis gap distance squared. So in this particular case, I x about this one, this is the x axis, equals bh cubed over 12, bh cubed over 12 plus area times this gap distance, which is called delta x. So that's the gap distance between the x bar axis and the x axis. Notice the gap distance will go in the y direction. So please be careful about that. Okay. And then Iy will be bh cubed, b cubed h over 12 plus area times this gap distance. Square of that gap distance. And notice it doesn't matter whether the gap distance is positive or negative. You will always add. That means the lowest moment of inertia is for the moment of inertia around the centroidal axis. Everything else will be higher. Okay. By the way, you cannot use it if you know the moment of inertia about this axis and you want to find out about that axis. You cannot use it. You have to, this axis always has to be about the centroid. Otherwise, you cannot use it. Now I'll show you how to do this problem for a compound object or a composite body. Then you will see how this works. Okay. Before we go, let's look at moment of inertia of some common shapes, because it's extremely useful. For a triangle, center of mass is here and its location is b over 3, h over 3. This is b, that's h. And then Ix is bh cubed. So around this center of mass, Ix bar is bh cubed over 36. Iy bar is hb cubed over 36. So for a right angle triangle, this is x bar, that's y bar. That's how it goes. For a rectangle, the center of mass location is there, and then Ix bar is bh cubed over 12. Iy bar is bh cubed over 12, b cubed h over 12. And this is b, that's h. For a semicircle, the center of mass is somewhere there. So this distance is 4 pi r over 3, and then the center of mass I, so think of this x bar, that's y bar, I x bar equals pi over 8 minus 8 over 9 pi times r fourth. I y bar is pi r fourth over 8. I'm just showing you what these things are, because these two things we will use very commonly. This occasionally we will use because many objects are made up of some combination of triangles, rectangles and semicircles. So it's very useful to have those things pretty much set. Okay, now let's look at something like this. Find the moment of inertia of this object around the x, y, around the x and y axis. You look at this thing and you're thinking, yikes, what do I do? So first step, break it up into combination of known shapes. Known shape means I should know centroid and I should know moments of inertia. In this particular case, what I'm going to do is I'm going to break it up like this. There's a triangle, and then if I break it up like this, there's a square and two triangles. And I know the moments of inertia of all of these. So we are off. So what we're going to do is we're going to look at this there. See, I've broken up into 1, 2, 3 regions, and the centroid of this one is here, the centroid of this one is here, and the centroid of that one is there. Can you see that? Those are the 3 centroids. I'm going to set up a matrix so that we can see where we are. So I'm going to do ID. So I'm going to have 1, 2, 3. Then I'm going to have the area of these, and this will be in millimeter squared, sorry, inch squared. So the area of the first thing is very simple. It's 36. Can you see 6 times 6? How about the second one? The area of the second one is base times height divided by 2, which is 6 times 3 divided by 2, which is 18 divided by 2, that's 9. And then the last one, base times height divided by 2, which is 9 times 6 divided by 2, that is 27. That's easy, right? Then let's find the centroids. I'm going to write down the coordinates of the centroid. So what's the coordinate of this point? That's in the center of this rectangle, and that's pretty easy. It's 3, 3. Can you see that? That's this. How about this guy? Right? The x component is 6 plus 1/3 of the distance from the base. So it is x component is 6 plus 3 over 3, comma y component is 6 over 3, 1/3 of the distance from the corner. So that turns out to be 2, so x and y components. Sorry, that's the x component, that's the y component, so it's 7, 2. Right? Do the same thing for the last one, and that will give me 8, minus 2. So that's the coordinates of this point. 8, minus 2. That's 7, 2. And then this one is 3, 3. You're with me? So we can calculate the centroid. Now we got to find, the next thing we're going to do is we're going to do axis gap distance. So this, for example, for this one, I'll pick a different color so that we can see what I'm talking about. For this one, this is the x bar axis. This is the x axis. So that's the gap distance. And this is the y bar axis. This is the y axis. That's the gap distance. Can you see that? So it turns out to be 3 and 3. That's the gap distance. Be careful about this one. The x bar to x gap distance is this height, which is 2. And then the y bar to y gap distance is that one, which is 7. So this will be 2, 7. Notice it's the flipped version of this. And the last one will be 2, 8. We don't care that it's in the negative direction. It's just 2 and 8. Okay. Now that we have done that, the next step is computing the moments of inertia. Ix bar, Iy bar. That's the next thing to compute. Right? For the rectangle, it is base height cubed over 12 and height base cubed over 12. For the triangle, right triangle, it's base h cubed over 36 and height base cubed over 36. Remember those two things, right? So we can go fill this out. So for the first one, it will turn out to be 432, 432, base height cubed over 12. For the second one, it will turn out to be 54, 445.5. This one comes from hb cubed over 12, 36, sorry. And then bh cubed over 36. Oh, I'm sorry, I got the numbers wrong. So if we compute Ix bar, Iy bar, it will turn out to be 108, 108. How did I get that? Base is 6 times 6 cubed over 12. That's this guy. And then this guy is 6 cubed times 6 over 12. Do the next one and it will turn out to be 18 and 40. This time it is, let's see, it's base times height over, that is these two things. And then the last one is the bottom two, which is 54, 121.5. Okay. So all I did was x bar equals base h cubed over 36 and Iy bar is h base cubed over 36. Okay, so compute this thing and I'll get these numbers. Now that we got all of that, what's our last step? Now we do parallel axis theorem. Ix equals Ix bar plus a delta x squared. Iy equals Iy bar plus a delta y squared. This is delta x, that's delta y, delta x, delta y, delta x, delta y. So off you go, and if you compute it, you will get 432 for the first one, 54 for the second one, and 162 for the third one. And then here I'll get 432 again, and then I'll get 445.5, and then I'll get 1849.5. That's how it goes. Okay, there are other examples, and there's actually many examples on the internet, so you can go and look at all of them. All of them work the same way. Okay, thank you very much.